welcome to my talk about Dirac-type results in hypergraphs. So let's start with a very old result, or two very old results, and let's start with graphs and not with hypergraphs. Two results you might all know. So first one, if you have a complete graph on an odd number of vertices, there's this very nice construction of Aleki saying, well, there is such a nice rotation trick will give you n disjoint Hamilton cycles, so S disjoint Hamilton cycles. And Dirac says, well, if you potentially don't have a complete graph, so much less structure, you might still have one Hamilton cycle if you at least can guarantee that the minimum degree is n half. So this is very old history. In some sense, we develop much further from then on. One direction is, for example, the result of Jaba, Kühnlo, Ostus, and Dracklaun, who said, well, let's say we want to have a Hamilton decomposition, so a decomposition into Hamilton cycles. What do we need? Well, we need, of course, that we are regular, or even regular, because if you take the disjoint union of edge disjoint union of Hamilton cycles, then you will be even regular. And if this regularity is then at least n/2, then in fact you always have a decomposition into Hamilton cycles. Yeah, so that's about decomposition of Hamilton cycles and graphs. But what about other graphs? What about much simpler graphs like a triangle? Yeah. Let's say we just want to have triangles, so very short cycle instead of very long cycles, so the other end of the spectrum, and ask for what is the right minimum degree condition to ensure that you can decompose the edge set into triangles. There are some very natural like divisibility obstacles here, which are somewhat obvious. If you want to decompose it into triangles, you better have that the number of edges is divisible by 3. And a little bit more complicated, but still very easy, consider a single triangle. It will either contain a vertex or not contain it, but for sure it will cover an even number of edges incident to every vertex. And hence it will always cover an even number of edges, and you better have therefore that each vertex degree is even if you want to have a triangle decomposition. Yeah, so there's other divisibility conditions if you replace triangle by something else. I won't spell that out in the following of the talk, but they are not very complicated, follow the same pattern. So given this question for triangles, which is still open, might be very ambitious to say, what about if we replace triangle by something else? Or yeah, so given the graph H, what is the best minimum degree threshold, or what is the best minimum degree requirement that still yields a H decomposition, subject to this divisibility conditions, obviously. And this is what we also call a decomposition threshold for H. So Nash-Williams conjecture says the decomposition threshold for triangles is 3/4. And yeah, so but even for triangles, this is already really hard. So let's relax the problem. So in a similar fashion as you go from integer linear program, you go to linear programming, you just ignore the integer requirement. So instead of saying you either take this triangle, you don't take it, you're allowed to take it half or a quarter or something like that. So you have the copies of H in G, or if you say for simplicity, the triangles, and then you no longer say 1 I take it or 0 I don't take it. You're allowed to do any fractional version of it, and you still require that if you look at a certain edge, that each edge is taken once, so that the weight summed over all copies of the triangles that contain this edge is still 1. And of course, you can also define then a decomposition threshold for this fractional version, which should be at most what you had before. And let's denote that by this additional star, so delta star H. Okay, so why is that now at all useful for the problem we originally had? And it's similar, yeah, the idea is similar as for integer linear programming. Sometimes the relaxation helps quite a lot. Let's have a look at two results in this direction where we gain some understanding from the fractional version to the integer version. So whenever H has chromatic number at least 5, one could say for essentially almost all cases, the decomposition threshold can only attain 3 potential values, or we know it's one of 3 potential values, 2 which are determined by the chromatic number chi, whatever it explicitly is, but 2 values most, or it's the fractional decomposition threshold. And Glock, Kuhn, Lowe, Montgomery, and Oskus also solved this entire question for graphs, for bipartite graphs H. And they have even further tools how to turn a fractional decomposition into an integer decomposition or a proper decomposition. So this gives us much more motivation to study the fractional version. And so again, so for bipartite graphs, we know it. For chromatic number at least 5, we also know quite a lot. So what about chromatic number 3 and 4? And let's start with number 3 first. Well, let's do only 3. And if you look at chromatic number 3 graphs, let's start with odd cycles. So what about cycles? As the talk is anyway about cycles, so this is a good point to look at cycles. So there's a theorem of Barber, Kuhn, Lowe, and Ostus who says, well, the bipartite graph is settled. That's either 2/3 or 1/2. And at the very least, we know for cycles, for odd cycles, then the fractional version or the fractional threshold coincides with the integer threshold. So also in particular for the Nash-Williams conjecture, is enough to now solve the fractional version, then you solve the proper Nash-Williams conjecture. So it's, if you want to try it, it's already a significant step simpler. Yeah. So, but we still don't know what's happening for odd cycles. And the first result I'd like to present today is joint work with my PhD student Markus Kuhn. So don't confuse it with Daniela Kuhn, which will always appear together with Derek Ostus. So this is the convention now. We proved that if you look at odd cycles, then the decomposition threshold actually tends to 1/2. It's somehow natural. If you think the cycle gets bigger and bigger, it gets more and more bipartite, or it gets closer and closer to a even cycle of length, let's say 2L, and there the threshold is 1/2. And this also solves a problem posed by Glock, Kuhn, and Ostus, who in particular asked whether this is true. But this is only a very special case of our actual result we prove. So let's, without any further ado, let's go to that. But for that, I need to say something about hypergraphs. Okay, what is a hypergraph? So I have a finite vertex set, and I fix some number k, and all edges have size k, which is then also a k-graph or k-uniform hypergraph. If you have now a vertex set of size m, and now think of m being smaller than k, then the degree of this vertex set is just a number of edges containing it. And of course, then it's not very complicated to come up with the minimum m degree if you just take the minimum over all sets of size m and then their degree. And often I will just ignore the index if the index is k-1. So one comment to this degree, what happens, or how are these different degrees related? Let's say you have a lower bound on the minimum degree, let's say minimum k-1 degree, it immediately gives you, so what does it say? Every k-1 set is contained in, let's say, x number of edges. What you can do is, if you have now a k-2 a set of size k-2, you can look at all k-1 sets, supersets, and then you have for that a lower bound, and this gives you then directly a lower bound for the k-2 set. So what I'm saying is, the larger m is, if you have a lower bound on the degree, the more structure you have. So it's natural to start with the k-1 degree because this imposes the most structure. So even very locally in every k-1 set, you have something, and it's far weaker to say something about the 1 degree, say. So just that at every vertex there are many edges. Okay, so this comments concerning degree. What about cycles? I focused on tight cycles in this talk. And that means I have a cyclic vertex ordering and always k consecutive vertices form an edge. And from now on, this will be just a cycle, always tight cycles in this talk. And a very classical theorem by now already is the analog of Dirac's theorem for the minimum degree being the k-1 minimum degree. And this ranges between 0 and n, n minus 1, or n minus k plus 1. So if you have there n half at least, plus a little bit, then you have a Hamilton cycle. For k equals 3, this error term has been even resolved completely by Rödl, Rosinski, and Semrady. Yeah, so this is one cornerstone result in the area. Also because of his methods, it significantly further developed the absorbing method. So if you don't know it by now, this is a very good paper to have a look at. And this is almost, well, I said if you have the minimum k-1 degree, this is far stronger. And our knowledge is only slightly beyond that, because only a few months ago, 2 groups independently proved that the best or the optimal value for k-2, and this 5/9 times the maximal value. So we are still lacking of a general understanding what is the k-10 degree, what is the right minimum degree threshold. So if we want to guarantee at least one Hamilton cycle, let's stick with the first result, that the k-1 degree is some value. Yeah, let's say n half in our case. Okay, so now I jumped quite a lot between Hamilton cycles, cycles of fixed length, now back to Hamilton cycles in hypergraphs. Now let's jump back to cycles of fixed length in hypergraphs. This is our first actually main result, and this is what we prove, that even for hypergraphs, if you look at cycles of fixed length but let the length go to infinity, then the fractional decomposition threshold tends to 1/2. And yeah, in particular, this holds then also for k equals 2. And for graphs for k equals 2, we know by this result of Bauber, Kuhn, Lowe, and Ostus that the fractional version and the integer version coincide. And yeah, so let me say I have prepared one slide to give you a good idea of the proof, hopefully. And I have 2 ideas, namely the restriction system and random walks. Okay, so 5 points. So one thing which seems very unrelated is the following. So think of a random walk, so a Markov chain on a graph. You are at a vertex, and then you go to the next vertex in the next step uniformly to one of its neighbors. And given this graph is regular, it's non-bipartite and connected, then actually after a long time, you're equally likely in every vertex. So you have a uniform limit distribution. So keep that in mind. This will be important in a second. So what number 2 is now, so what do we want to do? Let's say we're in graphs and we want to find a decomposition or fractional decomposition into cycles of long fixed length. And now we perform a Markov chain. Our states are the edges, and then we jump from one edge to the next edge by building somehow, hopefully, a cycle. And how can you jump from one edge to the next edge? Well, this is more or less a Markov chain in the line graph. So you have states or vertices for the edges, and then two states are adjacent, or you can jump from one to next if the edges are adjacent. The problem is now, if you in a view of number one, we want to have potentially a regular graph. We will see in a second why. But because the vertex degrees are away or can be apart by a factor of 2, our Markov chain is not or doesn't have a uniform limit distribution at the moment. So what do we do at every vertex locally? We just get rid of a few transitions. We say, oh, okay, here I have a clique in the line graph of certain size. Let's just take a subgraph, which is regular, and let's take deregular, and now take just d small enough that I can take a deregular subgraph in each clique, which sits on every vertex. This gives me a regular subgraph of the line graph. Yeah, so then in order to have a Markov, well, for technical reasons, we also need to have the states are now ordered edges, but okay, let's believe that this is somehow sensible. And now there's a key observation. So let's have this Markov chain where I walk on the line graph or a subgraph of the line graph, and I know that the probability from going from E to F in M steps is PM, which also depends on EF. But let's say this is just some value. This is equivalent of saying the number of walks you can go in your graph from E to F that are conform with this restriction system. So this, which don't use forbidden or edges we deleted in the line graph, is just this regularity or this degree in each of the subgraph to the m, the number of steps, times the probability. So you can somehow relate the number of walks to the probability. And then if you use now number one, because you have a regular graph, this Markov chain mixes actually rapidly to the uniform limit distribution. And it's independent of E and F. And in particular, you can take E equals F and calculate the probability that you're back at a certain edge after a fixed number of steps. This will be roughly the same for each edge. And this is somehow the same as saying the number of cycles that are conform with this restriction system is the same for each edge. And this is more or less almost a fractional decomposition up to some little error, which you can get rid of by local adjustments. So here the probability really helps us to find this decomposition. Okay, so this was the proof. So if you got lost, then you can join in here now. Let's revisit Rödl-Rosinski semi-ready. Yeah. So now I spelled out every epsilon and k. So for every epsilon, every uniformity, something holds for all large n. And what is that? If the minimum k minus 1 degree is at least 1/2 plus epsilon, and then you have a tight Hamilton cycle. So second result is joint work also with Markus Kühn and Bjarne Schilke, now from Hamburg. And we have almost the same. So we have for all epsilon, for all k, and then we even have an epsilon prime, which will help us, and something holds for all large n. So we have the same assumption to at least guarantee one Hamilton cycle. And in addition, we require the following. So we have that each vertex is roughly in the same number of edges. If you think you can even take epsilon prime being 0 if you want, yeah. But we allow some error here. Then you no longer just have only one Hamilton cycle, but you have a decomposition, approximate decomposition into Hamilton cycles. Yeah, you can decompose the edge set up to a small, up to 1%, say, up to epsilon fraction into Hamilton cycles. And there it's also clear why you need a second condition. So each Hamilton cycle, and for each vertex in that Hamilton cycle, so each vertex contains exactly k edges in this Hamilton cycle. So if you take the edge disjoint union of Hamilton cycles, you will be vertex regular. But and of course, so if you want to have a decomposition into Hamilton cycles, you should then better be vertex regular. But it's a very weak condition in a sense of, because it's a necessary condition, but it's just a 1 degree. So it's really just asking about the one sets, not the k-1 set. That's a big difference. And or if you want to also spell it the other way around, you can also say if the epsilon prime is 0 and you have a minimum degree graph, which is vertex regular, so each vertex is in the same number of edges, and you have this typical Dirac-type bound, then you can decompose this hypergraph into approximately into Hamilton cycles with arbitrary good precision. Yeah, this also gives an asymptotic solution to a problem posed by Klock, Kuhn, and Osthues, who ask a similar question for perfect matchings. And because also in hypergraphs, every Hamilton cycle can be decomposed into perfect matchings if k divides n. This also provides an asymptotic solution to their question, because they ask if you're vertex regular and have this minimum k-1 degree bound, then you have a proper decomposition into perfect matchings, and we have here Hamilton cycles. And for the proof, we in fact use the result we just had. So we first decompose it into cycles of fixed length but very long, and then we have a random process which somehow rewires or first cuts the cycles into path and then rewires them to obtain a Hamilton cycle, and then we use a certain random process to make that happen, even, let's say, simultaneously edge disjointly for each Hamilton cycle. And with that, I'm done. Thank you for your attention.
Thank you very much.
Thank you, Felix.
You're welcome.
Okay, we have some time for questions.
I actually have a short question, if you can remind me. So this fractional threshold and the integral threshold, they are exactly the same or asymptotically the same?
Well,
meaning for the graphs, for the cycle case, for example, odd cycle case that you mentioned.
Depends on the definition. So as I defined it, I already neglected lower order terms because
yeah. Well, I mean this plus epsilon, it stays there, or in the Nash-Williams question, for example, you want exactly 3n over 4,
that's
right?
true.
Not 3 fourth plus epsilon times n.
Yeah, that's true for the Nash-Williams. So I'm expecting here that it's not exactly the same. Their results. So this Bauer, Kuhn, Low, Osthues says it's asymptotically the same. So if you neglect little o of n, then it's the same. But because our understanding is still far beyond.
Because for some cases, as far as I remember, like for perfect matchings or for matchings in hypergraphs, I think it's Andrew Treglown proved that it's the same or something like that. Am I right?
Could be, yeah. I don't know.
Okay.
Hi, Felix. I have a question. According to Smith's theorem, a cubic graph, if a cubic graph has one Hamiltonian cycle and then it has another one. However, if given the first Hamiltonian cycle, finding the second one is a very difficult problem. Do you have any intuitions about that?
No, not from the top of my head.
Yeah, you give a lot of results about the packing number. But do you have intuition about the relationships about those Hamiltonian cycles? What's the structure relationship for them?
Not yet, no. So there's one more question in the chat. So what about a k-2 degree? So we haven't yet thought about the k-2 degree, whether we can, let's say we are vertex regular and have the minimum degree threshold for the k-2 degree, whether this then also gives approximate decomposition. Because both papers are pretty long, so 50 pages concerning this k-2 degree, I didn't yet dig into that, whether we can somehow make it stronger to actually get a decomposition.
Okay. So if no questions, then let us thank Felix once again.
Felix.
Okay, thank you.